This meeting is now being recorded.
If there's high surface temperature and you go to touch the combustion chamber on a metal stove, you're going to get burned. And that's one of the realities that we have to try to prevent. And the next one is actually the explosion of embers, because if small children go near the fire, they're in a small home, looking in the fire, and then a burning ember pops out, I've seen damage caused to eyes from burning embers actually coming out of the combustion chamber or around the pot on the stove. And so that's something we also want to prevent. And on the next one, scalds. So this is, the first one there is if there are handles or some type of protrusions around the cooking surface that stick up from the cooking surface. If you pick up the pot, you go to move it, it hits those little ledges around the cooking surface, and then you spill the pot, possibly on yourself or someone near. And then also one that's quite obvious is the second one under scalds, which is the stoves just have to maintain, they have to be stable, which also if they're not stable, it could spill out fuel, which leads down to some of the loss of property on the bottom as well. And I'll skip down the loss of property a moment. And so if I look at the large amounts of heat transfer to surroundings, that last one, in some situations, if the stove is placed too close to the wall, or if there's some heating unit that starts the fuel before you put it into the actual cooking stove, then it can ignite the surrounding combustibles or the home. Not that uncommon, actually. I had a family member, even in the United States, who lost their home from a wood-burning stove inside, fully enclosed, but the stove was so hot that it ignited the wood, the dry wood in the floor underneath. 2 hours later, entire house is gone. So this is not an uncommon problem, and we really need to look for that. The other one in terms of cuts, so we have sharp edges or points that can cause, lacerations, cuts. But then if the clothing catches on those sharp edges, then it can easily tip the cook stove over. So after looking at these hazards, I'm going to say, okay, of the available standards, how do those hazards, are they actually represented? And so we reviewed standards from a few different organizations. And the ones actually presented on the right, ISO, ANSI, and Underwriters Laboratories, those are the ones I focused on mainly when developing the set of 10 safety guidelines and metrics that I'm going to talk a little bit more about today. But this is the set. And if you want to look at the larger set of what I looked through is, and I don't expect everyone to be able to read this, but if you'd like, feel free to take a screen capture, as well as Rainey mentioned it's going to be online later and there's a recording. But these are 30 different stove safety protocols, or just protocols on, these are protocols on stoves that have safety included. A lot of them also have durability, because those two considerations often go hand in hand when developing protocols. Now what you see is, if I was in 2004 doing this, there are many of these. I updated this last time about 2 years ago. And so these 4 right here have been updated since then. These 3 as well, these 2, and going on up. And so a lot of these have been developed, and you'd expect that with the safety protocol I'll talk about today. And then Rainey will have some questions about way forward. Is there anything missing? Should we have testing equipment kits that we can send people, etc.? So that's kind of one of the ways forward. And if you take a look at this list as well, and you're saying to yourself, you know, we have a safety testing country that Nate doesn't have on this list, my email is going to be at the end of the presentation. Please send it to me. If it's in English, that's great. If it's not, we'll figure out a way to translate it, and we'll get it included. So that'd be perfect. So let's get on to the actual safety procedures that I developed. So why tiers? Why are we not doing this, a stove is safe or a stove isn't safe? And like I was mentioning earlier, is that let's see, I'm going to show presenters my cursor. Thanks, Laura. So what we see is that the incremental rating system is good for showing improvement. But then also is that the all or none approach, if we don't have an organization that's saying this needs to happen, and if you don't have it at this level, you're not going to be allowed to sell stoves, there's nothing out there like that in many countries. And so then that's another reason for the tiers. So people can say, well, my stove is at a fair, a fair rating, a consumer comes in and sees a stove right next to it is at a good rating, so it's like, you know what, if it's safer, then it's probably going to be good to purchase, good to fund, and it's a better design. So this is one of the reasons to go there. Now at this time, there was and there still is very little data on the likelihood of injury or the risk of injury. And so 10 years ago we were talking about, well, we can look at this qualitatively, and that's what I did. And so if I looked at the possibility of a minor injury and a major injury, this is how it ranked. This is at least how I set it up. So if on a minor injury, a poor rating would be if it was very likely to occur, like a small cut on your hand. But for instance, a major injury, such as what would happen from a skirt fire, if there's even a moderate chance of that happening, that is very bad, and so that gives a poor rating. And then you see how that goes down to the best. And many of the procedures that I'm going to show you in the next 10 slides have these 4 ratings to them, or in a couple more slides to come. So in establishing the tiers, there's a couple things that we need to consider. The first is we need a reference point. And so what is that reference point going to be? Where are we going to put the line in the sand and then work from there? So the line in the sand that we chose was actually the ANSI standard. That's that second bullet point. And so that is the, and this was identified this, proposed it to Ethos, and everyone said this is a good idea, let's go forward. And so the ANSI standard is used as a reference point. It's placed between the good and the best ratings. It's not placed at the top of the best rating because there really isn't a maximum amount of safety you can have. What is available, however, is that is considered the American National Standards Institute's minimum safety standards they accept. Let's put it between them, and anything that meets the standards, those standards, which also correspond to the same metrics or the same reference points and other standards throughout the world. If everyone is agreeing on that, that makes sense. Let's put the peg there, and then let's work from there. Let's work up and down. And develop those through collaborative discussion with stove community experts. So going through here, looking at the equipment required, the goal was to not require $10,000 US, $20,000 US to complete a test. I mean, we want to make it really simple, easy to use. You can do it in 90 minutes, and it's going to cost you, for a kit to do this testing, it's going to cost you something like $200 max. And most of that cost actually comes from the infrared thermocouple that I'll mention in a second. But obviously you're going to need the cooking equipment, and then the testing equipment is rather simple. This is a tape measure, a ruler, calculator to do some simple mathematics, cloth or rag, and I'll get to that in the first test. A piece of chalk, because you're going to be making grids on the stove, the floor, and the wall, and then testing the temperature of those. And then also a thermometer to measure air temperature, and then an infrared thermocouple to measure surface temperature. And if you haven't used one of these devices, it's extremely slick. And instead of taking a traditional thermocouple and then tacking it to various points on the cook stove, which is expensive, cumbersome, more cumbersome and time-consuming. And then also you need a reader to do all this. But if you have an infrared thermocouple, basically, if you haven't used one, this is a little gun with an infrared that goes and measures the temperature of the surface by the amount of infrared that's being released or that's being radiated. And so the thermal energy from the surface is radiated in terms of ultraviolet light, visible light, and infrared. Infrared is the largest of those wavelengths. This reads the infrared wavelength, converts it by a thermoelectric process into a small electrical difference, and that electrical difference translates and is scaled into the temperature reading that you see on the back. And so it's really, really easy. And so you can do really quick tests at all the points on the stove, etc., using one of these quite quickly. Looking at the safety tests, these are the 10, and I'll get into the details of these as we go. The first one is just covering sharp edges and points, cook stove tipping, and as you see on the asterisks there, those are the ones that were adapted or informed from the ANSI standards, and then there's 5 that I created new as a result of discussions and visits of my own of people in the stove community and visiting communities around the world. And then comes containment of fuel, obstructions near the cooking surface, and then 3 actually on the temperature of the surface, insulation to surroundings, so preventing against fires to the walls or the floor, for example. The temperature of the operational construction, which is slightly different than the surface temperature because you have to touch the handles, the operational construction, for a longer period of time than if you just accidentally brushed up against the side of a cooking stove. And so the restrictions on temperature is actually stronger for test 7 rather than test 5. Chimney shielding. So if the stove is safe from touching, what about the chimney? And is the chimney hot? And note, and I'll make note again this later just to remind everyone, if your stove is polluting, chimney is probably a good idea, or improve the combustion. But this test focuses just on the temperature of the chimney. It's not saying that you should or should not have a chimney. It's only saying that if you do, you need to check the temperature of it because people can easily touch it. And I've seen in many circumstances that there's actually a grate or some type of small wire with very small holes that's put around it that doesn't allow people to actually touch the chimney. I've seen that several times. And then you have flames surrounding the cookpot, and then the flames exiting the fuel chamber, canister, or pipes. And this last one, it was kind of a little bit of a reach that long ago because I was just developing these for biomass cook stoves. But I had people ask, what happens for solar stoves, and what happens for gas stoves, and methanol stoves, and ethanol stoves, and et cetera. And so this one was just a brief attempt to say that if you have fire coming out of any unexpected region of your stove, that's probably really, really bad. And so that's what this seeks to express and then rate for safety. So in terms of the first test on sharp edges and points, and each one of these tests that I'm going to go through has these 4 different basic elements. One is a guideline, then equipment, procedure, and then the metric. So on the guideline, the reason that I'm just not saying sharp edges and points and then going right into equipment or procedures is that if people just want to read through it for informative purposes, or if they don't have equipment to do the tests, they can still read the guideline and educate themselves on what are the dangers. So guideline, exterior surfaces should be smooth and not cut flesh. Okay, that makes sense. So let's round off those sharp edges. Let's use slightly different construction in this place, and let's go forward. Now, I said this was slightly adapted from the ANSI standard, and this is really just said that the ANSI standard said you shouldn't have sharp points, but they worded it in a way that's such, and this isn't that uncommon, is that the cooking device should be in a have quality workmanship, and that's not verbatim, but that's the gist of the actual wording in the standard, and that all fasteners should be secured, etc. And that is really hard to workmanship, translate across languages, across people with different backgrounds. If you're doing testing every day of the week, you probably have an understanding of what that means. But what I ended up doing, this is one of the simpler metrics, is saying, well, we can't really do that to translate this across and have it be a common understanding, but let's get a loose cloth or rag that would perhaps snag on the cooking stove. Let's rub that cloth around the outside of the stove, noting the number of times that it gets caught or torn. This is a relatively simple way to personify or to measure this idea of workmanship that we're trying to get across. And then you have the rating down there as well. So if it doesn't get caught, it's a rating of best. If it does get caught 4 or more times, then it's a rating of poor. And so this is test 1. Moving on to test 2. It looks like the PowerPoint didn't translate quite well if you look down there in the lower left. Hopefully that resolves itself later on. But if you look at this in terms of cook stove tipping, and so the guideline is cook stoves should not be easily overturned. And that has to do with, especially with larger cook stoves, that you don't want it to fall on anyone. Secondly, with the prevention of scalds from the pots on top. And then thirdly, if there's actually burning embers inside the stove that can fall out and start house fires or skirt fires, etc. The equipment is relatively simple. You need a tape measure ruler and a calculator. And the procedure here is I have in this diagram over here at the right. So you measure the height when the stove is not being tipped, and I always recommend to measure the highest point on the stove so you can get more accurate measurements when you actually go to tip. And when you go to tip, what will happen is you see that the small h is slightly less than the large H. And what ANSI ends up doing, or the other standards, is they say they look at right here, so you see where I have the cursor, and then if you go straight up, that will create an angle of 4, 5, 6, 10 degrees. And then they'll mention that given a static force of 50 pounds in this direction, the stove should not tilt more than an X amount of degrees. I'm like, that's interesting, but how many people have, I mean, it's great actually, but how many people have force gauges and can actually go through there and do that? And you might not even have a calculator that can do trigonometry to actually calculate what the angle is. And so what I ended up doing was, if you're going to take, so if this right here, and then you have this angle as well as the height, then you can take the ratio of those, and those correspond to actual angles as well. And so I just expressed it in a simpler way instead of having to do the trigonometry. People just do a small, simple divide, which it looks like we lost a little bit of the presentation here as well, but it's small h divided by large h. And then the one thing you'll note is that some cooking stoves are fixed or stationary, and since those are immobile, they receive a best rating because they can't actually tip. Great. Things are back in order on the placement of things, so it might have been hopefully just that slide. On the next one, containment of fuel. Guideline, burning fuel should have little chance of exiting the stove for obvious reasons that we talked about. Simple equipment, place a pot on the stove, and then you're going to approximate the area through which the fuel can be seen. And one of the ways you can do that is actually take a piece of paper and then cut it out, so it actually, on this cooking stove, is you would cut it out about that size. And so that's the area through which you can visually see the combustion chamber, and there's also some space over here. And then once you have that, you can use that by approximating that area using triangles, circles, squares. It's relatively simple, and then summing the area, and then this is the area that would be exposed. So obviously, if there's less area exposed to see the combustion chamber, there's less area exposed for embers to be expelled from the combustion chamber. And so this is the rationale and intent behind this test. And then going on to test 4, so this one is obstruction to the cooking surface, and this deals with the prevention of scalds, or even if your stove is lightweight and you go to move a heavy pot off of it and it gets caught on the cooking stove in some way, it could actually tip over the cooking stove, and then you have the same issue that we talked about with spilling burning embers onto the ground or onto skirts. So the general guideline is the area surrounding this cooking surface should be flat. Okay. And the procedure is we're actually going to measure the height of the obstructions surrounding the cooking surface. And if there's 5 obstructions and they don't have the same height, we're actually going to use the largest height in the rating because we want to understand what is the worst possible scenario. And so that's if one side is 5 centimeters high and the other side of the stove is 2 centimeters high, we're going to use that 5 centimeters, and then that stove would get a poor rating. And then if there's very little obstructions and the cooking stove is very flat, you have a griddle surface, there's nothing along the outside, it's very unlikely that a person is going to move a pot or some type of cooking vessel off of that griddle and then hit that obstruction and then spill the actual beans, porridge, whatever it's going to be. And if you note down here, and there's a few exceptions, one of them that we talked about earlier in test 2 was if it's an immobile stove, it can't tip, so it receives a best rating. There was some discussion at Ethos when I put this forward, and I recommended that skirt stoves, they're meant to be, the pot is meant to be rested down, but so people understand that they need to pull the pot out. But that skirt is likely going to be over 4 inches. But is that really poor? Probably not. And so I ended up putting forward the idea of, let's just call it a good rating. That's not a best rating because there still is a chance that the cook stove could tip over if people didn't fully pull the pot out. But since the stove is designed that way for heat transfer purposes, and there's reasons for that, let's call it a good rating, and people understood that and out of their heads and only went forward on this one. Going on to step 5, and now steps 5, 6, and 7 are completed actually with the stove cooking and operating. and stoves 1, 2, 3, and 4 were completed before the stove was actually ignited. These have to do with the temperature of the cooking stove, the surface temperatures around the cooking stove, as well as the temperature of the operational construction of the cooking device itself. And the simple guideline for this one is surfaces should not burn when touched. Okay, that makes sense. And the equipment is the chalk, the thermometer, and then that infrared thermocouple that I was mentioning. The next 3 tests use that infrared thermocouple. And if I was talking about an entire test kit would be on the range of $150 to $200, that thermocouple will be somewhere between like about 75% of that cost. And so it would end up costing you maybe $125 or $150 to actually get that device. That's the most expensive item, but it makes testing very easy and very quick for these next these next 3 tests. And so the procedure is that if you look at a stove, it's likely that the stove is not going to have a uniform surface temperature across the entire cooking device. And that makes sense. It's going to be hotter near the combustion chamber, hotter near the top of the stove, etc. If it has legs, it's probably not going to be hot at all for the legs of the cooking device. At least I hope it wouldn't be. And so the goal is here, we need to draw a grid on the cooking stove. And so let's make an 8 centimeter by 8 centimeter grid over the entire exterior of the cooking stove. And at every intersection between lines, or at every intersection between lines, that's where we're going to measure the temperature and see what is that temperature, and then compare it to the below table that I'll get to here in a second. And since the stove is probably not going to be up to its maximum temperature within 2 minutes of starting, I recommend that people heat for a period of about 30 minutes. And one of the interesting parts about this is that since we're dealing with wood combustion, different operators, different sizes of wood, etc., there's very, very little chance that you're going to get the same results every single time. And so this test, for instance, I've had people repeat as much as 4 to 10 times to get a better understanding and some statistics for what is this like under different conditions. And you would expect that too if you're using a wood fire, is that it may not behave the exact same every single time, which is why we end up doing multiple tests. So then we're going to take the temperature of the stove surface, the ambient air, find the differences between those, and then compare those down into this table here on the bottom. And the ANSI standard is mentions, these next 3 are adapted from there. The ANSI standard mentions that the testing environment should be 25 degrees Celsius, and then it gives the maximum temperature that the surface should be or will be. Now, it's unlikely around the world that every place is going to have climate control that can set the temperature to 25 degrees Celsius. And so instead, I said, well, that's unlikely, so let's look at the ambient air instead. And that's why we're measuring that and then taking the difference between those 2. And the reason thinking about heat transfer is why the temperature difference is important and not just the temperature of the cooking stove, is because if you look at the equation for heat transfer, it involves a difference in temperature over here on the left multiplied by the thermal conductivity of the material that you're actually contacting. And that's why you get these different ratings for metallic and non-metallic. And you could expect that is if, for instance, you get into a vehicle and you have, cloth seats, you sit down and it's comfortable, it's fine, it's hot outside, but it's fine, it's sun shining, but the cloth seats are fine. But then you go to grab the seat belt or the steering wheel or something that's metal, and it feels hot. Now the temperatures are the same, but the thermal conductivity is different, so the metallic object is actually going to conduct more heat or at a higher rate. And so that's why it's going to feel hotter. Now there's another thing with that as well, is that you see that if it's below what's called, I call the child line, ANSI just says if it's below, or ISO says if it's below 0.9 meters, there's these more strict guidelines. And so for instance, if the ambient air is 30 degrees, to get a best rating, the temperature of the stove should be, if it's metal, should be less than 30 plus 38, so that would be 68 degrees. The stove temperature should be less than 68 degrees if it's below 0.9 meters. If it's above 0.9 meters and it's 30 degrees out, and to get a best rating, the stove should be 80 4 degrees Celsius or less. And once you measure the stove on all the different points of the grid and then understand if this is below the child line or above the child line or if it's metallic or non-metallic, you're going to do several different comparisons throughout this for this one test. And you're going to take the worst rating that you find. And that's common throughout all the tests that I've developed, is that you're going to take one time through, you're going to take the worst, or what's the worst part of the stove, and that's going to express its safety rating. And to tell, again, if you're curious why there is a difference between the below and above the child line, that's because children are much more susceptible to burns. And the reason for that is if we look at the body composition is just different. For children, often they have a higher surface area to volume ratio, and so they can get more heat by contacting a surface, but they can't distribute it throughout their body as much or as quickly. The other aspect is that there's just more water in the skin, and so if there's more water in the skin, it's going to boil or get to a higher temperature rapidly and then lead to second-degree burns, which are blisters. First degree is just redness. Third degree is full degradation of the skin, possibly burning all the way down to the bone. And so then we want to prevent all of those, obviously. And then the third aspect of why there's a difference between the above and below the child line is that children have a slightly different physical composition underneath their skin. And so the types of fat and the types of acids underneath their skin are different as well. So given that change in the physiology between children and adults, the children have more strict surface temperatures. So if we do that, the stove's still on, and you can do 5, 6, 7 in the same, and I talked about 5 a good amount, so I can probably go through 6 and 7 a bit quicker, is that the heat transfer to surroundings should not start fires. And I've seen this happen, and I've seen it happen afterwards as well in many different parts of the world. Same equipment procedure now is that we're not actually testing the temperature of the cooking stove. We are testing the temperature of the wall next to the cooking stove or the floor underneath the cooking stove. So what I end up doing is I'll place the stove and where it's typically operated. And then I'll move the stove from the floor, or sorry, I'll draw an outline around the stove, move the stove away from that outline to another place, and then I go back to that outline of where the stove is sitting, and then I draw the grid within that. And so that's saying this is where the stove is going to sit. We need to check that. And then the same thing with the wall, as if instead of looking from the top and drawing an outline on the bottom on the ground, I'm going to look from the side. So I'm looking at the stove to the side on the wall, and then draw a silhouette around the stove on the wall. Pull the stove away, draw the grid, and then I'm going to put the stove back, heat it up again, give it 30 minutes, and then I'm going to pull the stove away. Obviously, if it's an immobile stove, you can't do this, but then pull the stove away, and if it's on a caveat, if it's an immobile stove, you're going to need to check within some distance around. Generally, what I recommend is 2 grid locations, so it's 16 centimeters, and so then it gives you 3 points to check. One at where the point of connection is with the immobile stove and the wall, 8 centimeters up, and then 8 centimeters up again, all the way for the length of the cooking device. Okay, but if you can move the stove away, you move it away, and then you take the points with your infrared thermocouple, just bam, 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 measuring them. And then what I do is I don't allow the cooking stove to be away from the cooking region for more than, I shoot for 30 seconds, but I allow it to a minute in some circumstances. And what this does is that after you move the stove away, obviously the temperature of the wall and the floor is going to start to come back to whatever the ambient temperature is, or the air temperature. And so you don't want to take 5 or 10 minutes to measure those, because then you're going to get readings that say that the temperature is less than what it should be. And you can hear the temperatures for those. You have ratings on the floor, and then you also have ratings on the wall. And I do this test if the cook stove is placed within 10 centimeters of a combustible, or if the combustion chamber is near the ground. So that's when this test is completed. And throughout, all these temperatures are expressed in Celsius. And then the next one is temperature of operational construction. And the handles basically shouldn't burn when you touch them. Same type of procedure. Take the temperature of components handled during use. And so if there is a combustion chamber that's closed but it has a latch on it, or an air vent that you open to get primary, secondary air, those handles are going to be used frequently during a cooking session. And if they're hot, as I mentioned, that's dangerous, and so we need to check those and account for that. Now, what's interesting is that it's not a simple brush against the stove, and I'm going to quick leap back. And so if you see metallic 32 and 20, so that's the poor and the best, I'm going to go back 2 slides, I think. There we go. Back 2 slides, and so if you see the metallic is 50 and 38. So this allows a higher temperature if you're just going to brush against the stove. But I'm going to go forward now. So if I go back to test 7, if you're going to be holding on to the to the handle for multiple seconds, you're going to get more and more heat to go into your hand. And as you get more and more heat to go into your hand, the heat needs to go somewhere. And so this says that you can hold onto the handle for a period of time, or and it's going to be fine. And that's really what this is getting to. And so if there's a lower temperature difference, and remembering that the heat transfer occurs between the difference in temperature between 2 surfaces, and since we're talking about conduction, the difference in temperature between 2 surfaces, and then the thermal conductivity between both of those, and then there's some thermal resistance terms, et cetera, which isn't particularly important in this discussion. But those are the primary movers. And so if you're holding on to a handle, and then you hold on to it for longer and longer and longer, at some point it might get hot, but for the time that you need to, and in your hand, you pull your hand away, but for the time that you need to use it, this is okay. So those are the 3 tests that have to do with temperature when the cook stove is operating. Chimney shielding as well. This one can be done as well with it needs to be done with the cook stove operating if you actually have the chimney. So if you're looking at the chimney, and this is Richard Grinnell from Helps International that I was mentioning about earlier. So if you have a stove with a chimney, and let's say, for instance, that it's made of ceramic, maybe that's going to be a bit not as hot on the outside, since the temperature is not going to be as much. But if it's metal, maybe it is pretty hot. And so if you look at the temperature of the chimney, and you say, wow, my chimney is really hot, and that's going to give me a poor reading on the temperature metric. So if you look at this and you say, oh, wow, okay, this is going to give me a poor rating for the temperature, and you want to say, well, you know what, although the temperature of that surface is hot, we can put a grate around it or some type of construction around it, shielding, to prevent people from touching it. And so although your chimney is hot, you could, for instance, have a grate with a really small hole where people can't stick their hands through, or shielding that people can't stick their hands through. And as long as they cannot touch the chimney, that's fine. And so this test I developed to account for stoves that were doing that. And I saw several stoves with that had high surface temperatures on the chimney, and through discussion, then they ended up going out and putting a shielding along that, along the length of the chimney. And as I mentioned earlier, this testing procedure has nothing to do with emissions. It's only about safety, and so that's what this says. If you don't have a chimney, you're obviously not going to get burned by touching a chimney, and so you receive a best rating. But I'm going to say it again. Note, we are talking about safety and not indoor air pollution. I am not advocating people to go out there and rip chimneys off their stoves because they're dangerous and causing burns. That is completely not it. Whenever you're looking at the performance of a stove, you're looking at emissions, safety, durability, and efficiency, and you need to consider all of those. The safety is just one component in an overall process that people need to go through themselves to understand, how am I going to best meet the health, safety, and satisfaction of my consumers. So that's really what you need to do, and this is just one checkbox in that entire process. The next one, getting on to the last two, the flames surrounding the cookpot. Obviously, if there's flames, this is a picture I took. I think this one was in Mali, actually. So if you have flames all around the cookpot, all the way up to the top, you're going to get your hands burned, or possibly your clothing, on reaching for the pot, stirring the ingredients, or your clothing could catch on fire. And this is just a metric by which to actually rate that. So obviously, if there's no flames in a region where you're going to be touching the pot or getting your hands, that's going to be great. But as you get, it's going to be worse the greater amount of flames that are on the pot. And I'm sure many people have seen it as well, is that this looks like a moderate amount of flames, but I've seen flames all the way over the pot as high as to here. And so if that's the case, I don't even know how you pick up that pot. And so that's a bit dangerous, and we need to account for that. The last one is flames exiting the fuel chamber, canister, or pipes. And so if you're a biomass cook stove, this is just another test that, so if we're looking at the last one was how much flames surround the actual pot. This one is how much flames exit the fuel loading chamber. And so this is really the goal of this one. And we want to measure both of those because they're not necessarily inclusive of one another. They're separate tests. Now, this is an attempt that I had made here to adapt to some of the people that wanted testing for gas stoves, but more importantly, the liquid fuel stoves. And so if you have a canister of liquid fuel and all of a sudden that canister is on fire, well, that's obviously really bad. And so that's why this rating just has two levels: poor if your stove's on fire where it shouldn't be, and then a best if it's in normal operating conditions. This, I would still just say there's so many more tests that are needed for electric, gas, and liquid cooking stoves that this doesn't fully encompass everything that's needed for that. But 10 years ago, the discussion, the sentiment was this is a start in the right direction, and we'll work to that later. And that was actually part of the IWA agreement, is that we recognize that these stoves get us a long ways towards biomass stove safety testing, but we need to expand this thinking to other cook stoves now that we have a base understanding of what's needed, not a base understanding, but a reference point of what's necessary, and then also some example procedures by which we can adapt, cater, and expand. So these are the 10 tests. Now once you have the 10 tests, if you took those, and there's 4 levels throughout, so if you took 10 times 4, the maximum rating that you could get is 40. Or the lowest rating, if you got a 1 for each of these, would be 10. Now in looking at this, what I found, and through discussion with people, is that that's great, but we also recognize that the tests, or the hazards themselves, have a different amount of bodily harm to the people using the cooking device. And so, for instance, sharp edges and points, if you get a small cut on your hand, maybe you need a Band-Aid. I mean, obviously there could be some issues, but it's getting infected, and that's something that you want to prevent. But that is less significant than having a pot of scalding water poured over on you, such as a cook stove tipping, or in terms of heat transmission to surroundings with starting a house on fire versus just getting a burn on your hand, which is surface temperature. And these are not meant to say that cook stove tipping is twice as bad as sharp edges and points. These are just relative metrics by which we can understand how does this relate to an overall sum, which we can get to an easy number that's easy to quantify and talk to people. And so if you take these 10, the average value between these is actually 2.5. And so if you take all of these, going through, but then actually you equate them, so you take a maximum of 40 times 2.5, there we go, you'll get a maximum rating of 100 points. And so with 10 tests, and then you get those tests, 1 through 4 rating, you multiply by each one of these, and you'll get a maximum rating of 100. And you'll get a lowest rating of 25. And that, I believe, gets us to the next slide, is on the overall safety rating. Now, from my thesis there, and you see the asterisk, that's the name, and you can easily tell by the length of the name why it's more easily called by its common name, Iowa State University Safety Protocol, is that I proposed 4 tiers. And at that time, a lot of people were talking about, is the stove good or bad? And I believe this is one of the first efforts to say, let's look at tiers, and let's actually have a rating procedure, and how are we going to go about developing that rating procedure and then implementing it. And these are the 4 tiers that I put forward. And if 25 is the lowest rating, what you have here is that between 25 and 76, that would be a poor, and then between those two numbers would be a fair, good, and then best. And that worked out pretty well. But what's interesting is that initially, I tested, I believe, 15 biomass cook stoves with the procedures, and I got tests from other people as well. Is that over the last 10 years, we've been able to expand that to 50 and 100 stoves and get more information on how people, where the stoves actually rank. And it was really informative that through the IWA process and before that with the Lima consensus, for example, that there was some more discussion then for how about for all of the tests, how about for emissions, for efficiency, and then also for safety, how about we all use a tiered rating procedure? And there was a movement towards, for those emissions and efficiency, let's go for 5 tiers. And since my work had 4 tiers, a group expanded those 4 tiers and actually created another one right here. So now you have a tier 0 and a tier 1. And this tier 0 is really 3-stone fire or open fires. And tier 4 is something that everyone's striving for. And so that's what everyone wants to get to. And then it increases as you go up in scale. Now this is great because if you look at this next couple slides here, which I have some of the results from different cook stoves around the world, and these are at Iowa State University, the Engines and Energy Conversion Lab at Colorado State University, and Appalachia Research Center up in Oregon. And I have test results from several other labs around the world, as well as the certified or the labs that are that have won grants also from the Global Alliance for Clean Cook Stoves. And so this is really becoming a global effort and a global sharing of where we're at, what knowledge do we have. And you see here open fire, so we have open fire, a single pot traditional stove, a single pot improved stove, and then a multi-pot improved and a griddle improved. And this is how the safety goes up over time, or not over time, but as the devices change. Open fire, obviously extremely low. Then you get to a single pot traditional, often the handcrafted that you'd find in a marketplace. Single pot improved, maybe people would make it in a marketplace, but more often this is getting to where we're talking about the larger manufactured stoves, whether they be a couple hundred a month or a couple thousand a month, for example, or tens of thousands a month. It's kind of getting into that range now. Multi-pot improved and griddle. Now if I just add some lines on there, I think this will make it a bit more illustrative. So where do these rank for the 5 different tiers? Open fire, obviously in the 0 tier. And so the development of those 4 tiers and movement into 5s is actually really effective to show how safety improves and where things rank for the different types of stoves. And as you see in these, if you haven't seen a box and whiskers plot before, that's what it's called, box and whiskers. And these don't have to do with averages and means, etc. These have to do with where does the data rank in the data set. And so, for instance, a single pot improved, if this has 13 data points, and this is the median, this would be the 6th highest value that was rated for a single pot improved. As we go up, this would be this is the upper quartile, so whatever 75% of 13 is, we're talking we're talking like 8 right there, 8, 9, and so that's one of those values right there, and 8, 9, 10 right around in there. So you have those, so you have that number 9, and then it goes up, and then this is the maximum value observed. So the maximum value observed here was 95, and the lowest value was 71. And what's interesting is that if you go up even more to the griddle and improve, is then you look at this box and whiskers graph, what you find out here is that the median actually coincides for the multi-pot improved and the griddle improved fairly well with that bottom of the 3rd tier. And so what we can say is that from the tens or a couple dozen of the stoves that we have data on right now for the multi-pot improved and the griddle improved, about half of those stoves fall into the tier 3 and the tier 4 category. All of that upper half for the multi-pot is in tier 3, whereas if you're doing a griddle, you get an increased safety in some reasons. That is generally due because if it's a griddle, there's no visualization of what the combustion chamber is, and so there's like very little area by which embers can come out. And often the surface temperatures can be a little bit less on the exterior because you're using thick construction to hold up that griddle and to hold up the pots on top of it, and thereby you get better insulation, etc. And these kind of how they rank. Single pot traditional is largely in the 2nd tier, then, as I was saying, open fires in the bottom. And so this really starts to give us some evidence on what types of stoves, where do stoves rank in there, and where can we move from here. And so this is an excellent way to compare cooking devices. Going forward a little bit, benefits of these protocols, like I was mentioning, there's an aggregate safety metric. And so we can say the stove is 80, the stove is 90, the stove is 85, and that can guide consumers as well as funding agencies. Additionally, the individual 10 safety metrics demonstrate how designers can improve stoves. So if the cook stove is good on another metric, but it tips easily, if they want to bump themselves up to another tier, they know that they need to focus on the tipping hazard. And so that they need to, for example, expand the base of their cooking stove so it doesn't tip as easily, or make it heavier on the bottom and less heavy on the top. And then what that'll do is the goal of that is to also say that you may not have an added cost by introducing safer technologies, such as by widening the base. In keeping with the goal is that I was trying to make these metrics very pragmatic, easy to use, require little technical expertise, relatively easy to translate, very low cost, because the goal here is to promote use and not to restrict stove design and stove improvements and stove sales and benefit to consumers. The goal is to benefit consumers by making it easier to use, by making it pragmatic and making it low cost and easy to use. And it takes about one to two people about 90 minutes to complete. So a little bit on the way forward. Where we are today, 10 methods, principally for biomass, focused on handmade stoves, used in over 15 countries. As I was saying, it's accepted in the International Workshop Agreement of the ISO process. And my email is going to be coming up later, but it's right currently in review as part of a book chapter, and then it's going to be soon submitted as a journal article. So in addition to the thesis, if you don't look through the 100 pages, feel free to let me know, send me a note. That has all the background, but it's going to be consolidated into these forms of publication as well. So that works, and it's translated into Spanish as well. So if by some fellow workers in Bolivia, so if you want a copy of that, I'm sure that if you email me, I'll put you in contact with them, and they would be more than happy to provide that to you. Obviously, we're not at the end of the line. With stove standards, even that they started in the 1960s in ANSI and ISO, those are still being revised and updated today. Their cook stove standards are meant to evolve, which is why they have a year with them. They don't just have, this is what it's going to be for all time. As we learn more, technology changes. And there's a few things here for continued work. Laurel, which we'll talk here shortly, has excellent data entry sheets for these current tests that will allow people to enter data, and she's going to talk more about those, but that's a fantastic start to let's gather more data and understand stoves throughout the world. We do need additional tests. And after these 10 tests, I actually went back a few years ago and identified 23 hazards that we need to really look at. One of those includes pinch points, for example, that isn't included. And also there's this durability and safety relationship. For example, that after a period of thermal cycling, the quality of the stove may degrade, and thereafter may increase the likelihood or the chances of the stove falling apart underneath a large static load, which is another test that we need as well. But that's a pretty coupled durability safety relationship that's going to be interesting to pursue. Principally for biomass stoves, I had people request for how does it relate to solar stoves, but that wasn't a direct there's things that worked well, but there's things that didn't work well, and so instead of overreaching with the protocols, I said we're just going to stick to biomass stoves and develop the rest later. Possibly, and these are a couple questions, and Rainey's going to have a couple questions at the end. Do we need to extend these procedures using more expensive equipment, for example, and be completed in the lab? Or are we good with where we are, and should we package up equipment and send these out at a low cost that people can actually go buy, or should we just have instructions for how they can assemble testing kits? And should we look at hazards of fuel collection, storage, and consumption, for example, especially with liquid fuels? The consumption of those is quite dangerous. This is a picture I took in Vietnam that I think I just want to show you really quick. So under accommodating more stove fuel designs and fuel types, if you have this beehive charcoal stove, okay, most people think they're going to test this, but if you haven't seen this device right here, which my current cursor is currently pointing at, this is a small electric coil that you plug into the wall, and then once you plug it on the wall, it gets quite hot and starts it basically starts this beehive charcoal on fire, and gets it burning, gets it going, and then you drop it in, and then it burns from the bottom instead of trying to light it using matches, etc., which is going to take quite a lot of time. Now, these are relatively common. I've actually seen these. I've been in houses when these have started fires, like actually in the house, and the house is on fire. I have seen this happen. And what happens is these get so hot and they're so near the ground that anything underneath the ground, even if it is just wood, I'm not talking about agricultural waste or splinters of wood. I'm talking like a plank of wood or OSB or something. If you put these on top of that wood, it will start the wood on fire. And it doesn't need to be in contact. It gets so hot so quickly. And so that's a hazard that's definitely not represented that needs to be considered. Here's my contact information. Again, my name is Nathan Johnson. Feel free to send me a note at Homer Energy. And then if you want to look up the thesis, it's posted several places online. It's free to download. Feel free to go there. But if you want a copy, send me a note, and I will send it back to you. And I think at that time it's actually good that I can segue into Laurel, who will talk a little bit more about the summarized procedures and the data entry sheets. So Laurel, I'll hand it over to you.
While I change the audio, this is Rainey Chang again. I'm just going to introduce a little bit of the motivation for what's going on in some context as well. So for, Nate has worked on developing the procedures for testing, and he mentioned one of the pieces of equipment that was needed was a calculator. And so what Laurel Hamilton, who is an intern with the Global Alliance for Clean Cook Stove, she's been working on a spreadsheet that can be used where you enter the measured values and then the results are calculated automatically. And this is also a way to help us standardize how the testing is done and also integrating the data together when it's done. And I wanted to let people know that this spreadsheet that Laura will be talking about, we are still working on some final issues with the spreadsheet, but it will be posted online. And for all the people who are joining the webinar and others as well, we will share the link for how to download this spreadsheet. So Laurel, you should be currently unmuted.
Okay, can you hear me?
Please go ahead. Yes.
Okay. So thanks for that introduction. This will only take a few minutes. We just wanted to share with you all what the tools look like that we're trying to develop here at the Global Alliance for Clean Cook Stoves. So I just took all of the hard work that Nate did for his thesis, pulling together all the information that there is out there on stove safety testing procedures and put them together in a couple of easy-to-use documents that could be used in the field. So there's two different tools. The first is just this guidelines document, and it would outline how the test would be done, as well as the equipment that would be needed and a step-by-step procedure. And there's a few of them that include these nice pictures to help show people what they should be looking for. So that's for all 10 tests. And then we also developed this entry form spreadsheet. And you can see at the bottom, there's just 3 tabs. The first tab is just the general form for who you are, where you're testing, what stove you're testing, and you can just enter all that general information. And then you would click over to the test entry on the second tab, and that would have a place for you to put your measurements for all 10 tests. So we developed this with the idea that you wouldn't have to do very many calculations using this spreadsheet. I've inputted all those formulas that Nate talked about for how you would get a rating based on your measurements. So you would just enter in the gray areas here for each test based on the procedures in the guidelines, and then it would automatically come up with a result for each test on the best to poor scale. And then from that, the third tab on the Excel spreadsheet would be this tab showing your results, and this would just be all automated. You shouldn't have to plug anything into this form. So all of your ratings from the 10 tests would automatically show up here in the second column, and that would be multiplied by the different weights that Nate talked about and come up with a value and a total sum, which then could be calculated automatically here into the stove rating overall and a safety tier, which is linked to the IWA ISO standards. So with that, I hope that that's helpful in just showing you all kind of what we're working on and what it would look like in the field, and we wanted to get your different input and ideas on how this could work with your different experience in the field. So we have a few different discussion questions here. Rainey, I don't know if you wanted to talk about these or I can just read them.
Yeah, I'll go through the discussion questions, and one more comment about the spreadsheet. For those of you who have used the water boiling test spreadsheet, it's quite similar in the motivation for the spreadsheet, in that there are pieces of information that are entered and then that they are then calculated. We will also be making sure to keep track of the versions of the spreadsheet as there are changes and updates to that. So we will try to let everyone know if there are updates to the spreadsheet and keep track of which version of the spreadsheet is which. And so that file will be available soon to everyone. And really the goal of this whole webinar is to have more people be able to be doing testing on stove safety, and the spreadsheet is to make that job easier for you guys as well. Before I get to the discussion questions, there are a couple questions that came in. Jim Jetter has asked, do you know what are the typical costs to have a wood-burning stove or a cooking appliance certified for safety per ANSI?
For me, Jim, that's actually a really good question, and I don't have that number with me right now.
Do you have an approximation or?
I mean, I've been given figures because you go through the pre-certifications. So you have the people in your lab that do the testing, and then you go out and you contract that with an external lab. And I've heard ranges anywhere from 4,000 for up to 15,000. So. And I haven't actually gone out to a lab to say, here, I have a stove, please certify this, and so I might even get different values myself.
And then one more question about electrical safety. Jim says that they've seen some stoves with electrical fans with uninsulated terminals, and there's the risk of electrocution.
That's a very valid point, and I've seen that in several places as well, and stories of children, for instance, playing with the open electrical wires and then getting electrocuted. And that's definitely an important point that you're right, Jim, that it didn't fall out of this discussion primarily on biomass stoves, but if we move towards looking at electrical stoves, that's something for sure to look at.
And then going on to the discussion questions to trigger some maybe additional questions from the group. We've got 30 people on the webinar, so a lot of potential for interesting suggestions and questions. So the first is about, the first two are coupled together. It's about conducting the protocol. Are there questions about conducting the protocol that people have, or questions about the equipment, or whether you have the current capacity to conduct the protocol?
Are we
All guests have been unmuted.
So right now everyone is unmuted, and I do hear, it sounds like a few people have their lines unmuted. I would suggest if you would like to make a comment or a question, unmute your own phone. Otherwise, please keep your line muted. And while questions are coming in, perhaps people are typing as well. the next set of questions, the third and fourth questions, are related to what you are all seeing in your particular region. So Jim asked the question about electric fans on stoves that might have risk of electrocution. So that's a particular challenge that they're seeing that's not covered by the test. Are there other safety issues that you guys are seeing that aren't covered by the test? Or are there particular types of stoves or fuels that might provide challenges for the current testing procedure? And then we have a question from Chip Withers. Has there been any discussion regarding any type of fire suppression systems in case there is a cook stove fire?
That's a good question, Chip. There hasn't been any discussion about it. I think it's an interesting thought. But if the cooking devices that everyone's designing is somewhere in the range of, $100 down to as low as $4, having a fire suppression system is probably outside the available cash to actually implement cooking stoves into low-income family households.
This is Chip. Can you hear me?
Yeah, hi, Chip.
Hey. Boy, great presentation.
Thanks.
I had been research training a while ago. I'm with the COPD Foundation, and we discussed about donating fire blankets out of a material that could be packed very lightly with the stove. They weigh probably a half a pound, and again, the COPD Foundation would donate them. And they could be packed in with the stove. They don't need to be translated in any language because you have a stick figure that basically opens up about a 6x6 piece of, it's kind of like a fiberglass material, and you just set it over the fire, and it immediately distinguishes it. No wire, no pressurized fire extinguishers to maintain or anything like that.
That's a really good idea. I like that.
Well, if you do, I'll send you a couple samples, and again, this would be a program that the COPD Foundation would be a part of, and we would fund it. So
that'd be perfect.
And we manufacture them now in China, in India, and also with Goodwill Industries in the United States, and so we could design the packaging and whatever. Should I shoot you one?
Thanks for sharing that, Chip. And I think some additional issues to think about as well are the sustainability of this approach and affordability. I don't know how many the COPD Foundation would be able to fund and support, but I think long term as well, what are the options for making sure it's there's a sustainable supply and market, and as well this input from the stove manufacturers and distributors about their thoughts on having another product packaged with their product. So other issues to think about and consider. We do have a question from Tim Longwell from Zamorano. With chimney stoves, there are some models that have a brick base for the first 25 centimeters above the cooking surface, thus out of reach of children and reduced risk during typical cooking activities. Should this brick base be taken into consideration?
Yes, and that brick base, anything that's on the entire stove, including the surfaces surrounding the combustion chamber, et cetera, as well as the chimney, the entire stove should be tested up to a height of 1.5 meters. And then depending on if the material changes on the chimney, that's fine, and you'll look at the test and say, well, we're measuring at this height and it's of this material, and then that's what will correspond to your end metric rating. But that's a very good question.
And I also flipped to, Nate, the test entry form that shows the surface temperature section with the below the child line section above the child
perfect.
line.
Exactly. So over there on the right, as Rainey was mentioning, there's so for instance, if the brick material goes up to 0.8 meters, then you still have 0.8 to 0.9 meters that would be below the child line, and so you'd have to measure that metal part as well. So if you have any other questions on it, shoot me a note and I can talk to you a little bit more about it.
And we have a question from Christian Lorange from Colorado State. Dr. Lorange, when conducting the tests, did you have local cooks operating the cook stove, or was it the testers? And how much of a difference did you see in the results based on who was operating the stove?
It was a bit of both, and the main difference that I noticed, largely it was just the testers and local people cooking inside the home. But what I did notice is that generally the people cooking inside the home use larger fires, actually. And so that's an important thing to consider, is that if the testers are actually stoking the fires to what they consider to be reasonable, that may be different than if someone is in the household and needs to step away for 15 minutes and wants to shove as much wood as possible in there, and then 5 minutes later you have a very large fire. Not saying that's a house fire, but just like the stove is very, very hot. And that's the biggest difference that I saw. The rest of the tests cover it because the stove isn't operating, so there's no difference than if it's really who's doing the test. But once you're actually cooking and stoking the fire, that's where I saw the difference, and that's a really good question, Christian.
Yeah, this is Tegeke. Can you hear me?
Yes, we can hear you. Please go ahead.
Yeah. Jackson Tegeke from the I'm asking, would there be some stoves which would be not considered by the test protocol because for some elements the containment doesn't apply to charcoal stoves? It is obvious that the flames always get out. So would there be a procedure whereby some lights are exempt?
It sounds. I apologize, but it sounds like your line is breaking up. But
Jackson,
all
can
I heard
you type
was
your question in?
Yeah, perfect.
And then Jackson, while you're typing the question, I did want to make sure people saw the comment from Elmar about how they've translated the summary guideline into French, and they'll be using it in a workshop coming up in West Africa with colleagues across multiple countries, and then we are also working on making that available as well, along with the materials that Nate and Laurel have developed. So when we send out the information about the recording of the webinar, we'll also send links to all of the different files, including the spreadsheet and the French version as well. And sorry, Nate, you were saying something?
Yeah, Amar, just that's excellent to hear. I'm always really happy and enthusiastic when I hear people using the test and then also translating in other languages. And I thank you for doing that. It takes an immense amount of work, and I personally don't have. I'm just conversational in French and Mandarin, so I would not be the person you want translating. But I'd love to hear a bit more about your work. Send me an email. I'd like to catch up.
And then an additional comment from Tim. He was referring to the chimney shielding test in particular, about the height.
What's the question?
The question was about the brick base for the first 25 centimeters above the cooking surface. And
Okay.
it makes the chimney out of reach for children.
I think I answered that one earlier, and if there's any part of the stove that's less than 0.9 meters, it's technically considered within a child's reach. And I'm not trying to say that if a child is 2 years old, 4 years old, or 8 years old, obviously they grow in height and they can reach higher. But 0.9 meters is the line that's been adopted as many national standards and internationally as here's what is a reasonable height that a child can reach. So I would encourage you to continue to utilize that metric.
And it looks like Spanish as well. Thanks, Tim. And Jackson, are you typing in the question?
I'm not getting the audio properly. I can only read the text. I'm not getting the audio.
Oh.
I can only type in the text. I'm not.
To me?
Yeah, please. I have to email the question first. I'm not getting the audio at all. It is on and off. I actually didn't even hear.
Okay, yeah, I think, Jackson, we're going to have to follow up on email, and then we'll connect with Nate as well and make that available to any others who are interested. Any other questions?
I have a question chatted from Gloria. She says,
Yes.
Is it acceptable to treat this protocol the same as others we discussed the Malawi standards for stoves, or should we wait for the very final version?
In the what standard, sorry?
She's talking about the IWA standards for Malawi, I think.
Okay, I'll probably need to learn a little bit more about the situation, and I'm not saying that anyone needs to use or not needs to use this in any way. I would recommend it because it's the only thing we have out there that's easy to use and covers a lot of the issues that would be presented. So if you're looking for my advice on if it should or should not be used with the IWO process, well, the community that was there said that out of the tests that we have available, we're going to move forward with a certain number of them. One was looking at emissions, one was looking at efficiency, and then one was looking at safety. And so this is the protocols or the guidelines that were put forth by that community for safety. And if you'd like to take their recommendation, which I suggest you do, I would go forward with this. But if you're looking for other protocols or needs, it's not uncommon, for example, for a manufacturing firm to have additional protocols in-house that they also do for example, what Jim was getting to with the fan, for instance. The electric fan is not included. So if you're a multi-billion-dollar multinational company developing this and you're meeting international standards regardless of what standard is available in the local community, you're going to be concerned about, can that fan electrocute someone? So you're probably going to have additional tests outside of these as well. So that's kind of a broad brush response to another really good question.
Yeah, and to add a little bit to Gloria's question, so the IWA is at the international level, and Gloria, we haven't talked in a while about what's going on in Malawi and whether any of the IWA components are being adopted within Malawi. In terms of the protocol updates, the updates that Laurel has been working on are to provide an easy way to do the data entry and the calculations for the results. It doesn't change the protocol or how it's tested. It's to facilitate more and more people to be able to do the test. If there are updates to the protocol, that will probably happen with any protocol. The IWA is one point in time, and that's fixed. But the international standards process will continue in terms of additional protocol development and the standards being updated and refined and formalized based on additional progress as well. There's a question from Jim on the chimney shielding. A 10 square centimeter opening is big enough to put a finger through. Is the distance between the shield to the hot surface also considered in the protocol?
I think it's an important metric, but it's not listed in the protocol. And one of the reasons that I'm looking at that is I was trying to make this as easy to use as possible. And so now we're talking about, and it's a good question, but now we're talking about different ages and different hand sizes and different lengths. And so then all of a sudden we have, if we're looking at a chimney, what I have on there is the temperature of the chimney and then the size of the holes for the shielding. And now we would additionally need something that relates the temperature of the chimney if we want to do the finger length or the distance between the shielding and the chimney. If we wanted to do that, we would also need to now have a more complex multi-vector table that says if you're a child, you're at this temperature, but your child's hand is, your fingers are only 4 centimeters long, for instance, versus an adult, which might be 6 centimeters long, and an adult has a different temperature associated with it. And so that got to be a little bit more complex, and I tried a little bit with and worked with some people, and it was just a bit too cumbersome. But it's a really good idea, and if we move to something that isn't a 90-minute test done in the field, and we want to move to something that's a laboratory test that takes a day or several days and costs more money, we can easily include considerations such as that.
It's now after 10:30 here, which is the scheduled end time of the webinar. If there are additional questions, please send them in, and we'll stay. Nate, hopefully you can stay on for a couple more minutes if there are additional questions. But I also wanted to thank Nate and Laurel for presenting today, and hopefully we can have more and more testing that's done for safety of stoves and fuels. And thanks to all of the participants as well for contributing great questions. And we're looking forward to the next steps and hearing additional feedback on the protocol.
And I'd like to add to that with Rainey is, also thank you for everyone who's coming out today. It's a topic I enjoy talking about. And so it's great to see everyone here, have the questions, and then thanks to Rainey for setting up the webinar, and Laurel for all the work that she's doing in taking the thesis document and the testing procedures and putting that into an easy-to-use Excel sheet. That'll really be great to get results from everyone so we can start to make some more and more international comparisons. That's fantastic. And I guess I can stick around for a little while if people have more questions.
I don't see anything else coming in terms of the questions.
Okay.
All right, thanks, everyone.
Well, thanks, and I'm logging off.